All right, hello, we're going to solve this initial value problem. And to do that, we're going to use some formulas here. We're going to use the Laplace transform, which would, I guess, most likely not be the fastest way to do this, but it's an exercise. Here we have 0 on the right-hand side, which tells us that maybe we wouldn't really have to use the Laplace transform for this problem. But we're going to use a formula that the Laplace transform y prime is equal to s y of s minus y of 0, where capital Y is the Laplace transform of little y. And then we have Laplace y double prime equals s squared y of s minus y minus sy of 0 minus y prime of 0. So we'll start off with those formulas and apply the Laplace transform to this equation here. And as we go, just try to pay attention, not make a mistake anywhere. So we use linearity to break up this Laplace transform. So, all right, so I'll use the formula now. So I have s squared y, I just write y instead of y of s, minus s y of 0 minus y prime of 0 minus 2 y sy minus y of 0 plus 5y equals 0. So y of 0 is 2, y prime of 0 is 4, y of 0 is 2, so I get s squared y minus 2s minus 4 minus 2sy plus 4 plus 5y equals 0. I'll group those terms that have y and what we do see is that there's a little bit of cancellation. Fours cancel out. So then we get factoring out y. So y is equal to 2s over s squared minus 2s plus 5. And all right. So what we want to do is actually, if we can, what we want to do is factor. So factor the denominator. It's a rational function. We're trying to find the inverse Laplace form. So we're going to find the inverse Laplace transform. But, okay, this is a rational function. So we're going to try to either factor the denominator, or as is the case here, what we're going to do is, since it doesn't factor over the real numbers, it's irreducible. What we're going to do is we're going to complete the square, which is, it's an old trick, but maybe you haven't done it in a while, but it's an oldie but goodie. So we take the coefficient of s, which is -2, divide by 2 squared, and that makes 1. So I've just introduced 1, I subtract 1, because 1 minus 1 is 0, and I have 5 here. So I have y equals 2s, s minus 1 squared plus 2 squared. And, okay. So let's just see where this goes. Now, the thing is that we have more formulas, that the Laplace transform of e to the at cosine bt is equal to s squared plus b squared in the numerator. No, it's not quite that. So it's going to be s minus a squared plus b squared in the numerator, s minus a. And then Laplace transform of e to the at sine bt is equal to b over s minus a squared plus b squared. So all right, so there we go. Okay, so the thing is that this is not quite in the format we want, because we have s in the numerator. We want s minus a, where a is -1. So we do this little trick here. We write 2s minus 1. And see, since I've just... Do you see what I've done there? Is I subtract 1, but it's not really 1 actually, is it? This is 2 times -1 is -2. So what I do is I add 2 back. So this is y equals 2s minus 1 over s minus 1 squared plus 2 squared. And then 2 over s minus 1 squared plus 2 squared. And so then we do the inverse Laplace transformation, and we just use this formula, these formulas over here, and we get 2 e to the t so in the formula a is 1 and b is 2. Cosine bt, and I also have a 2 out front, and then plus sine plus e to the t sine 2t. And you could verify your answer. Especially easy is just the first one. If I put in t as 0, I get 2, and then it can be shown. You take the derivative that you take the derivative and put t equals 0, and you'll get y prime of 0 is 4. It's going to be a little more of a challenge to show that it satisfies the differential equation, but you can do that. So you can check the answer. Okay, that's all.